In the first lab, you got a hands-on feel for what goes on when you use applications like web or SSH, or even when you ping machines. You also got to experience some really cool networking tools like TCP dump and Wireshark. In this video, we will look at another useful tool in the area of networks, that of network simulator. While there are a bunch of commercial network simulators, the simulator which we will explore is called ns2. It stands for Network Simulator version 2. This is an academic effort basically maintained by some groups in universities. You as a student can also write code and contribute it to ns2, in which case others will use your code when they are running ns2. We covered briefly the need for simulations in the earlier video. In this, we'll go into more details. If you don't have any money, this is the way to go. ns2 is free. All you need is a computer to run the simulator on, and you're all set to run experiments involving hundreds of nodes. If you're trying to test a complex scenario via implementation, I can assure you that soon you run into a lot of problems. Real products don't work the way they should. Some code will be in kernel space, some code will be in user space. You need to figure out how to integrate things. So implementations are in general very complex. So the same scenario can be very easily tested through simulation. Also, if there was a project and one were to do simulation of it and one were to do implementation of it, the simulation would easily give results much faster, where the simulation can potentially finish in a few months, whereas implementation can even take a few years. There are also cases where you want to test this really advanced concept and you may find that there is no hardware out there through which you can test. Then the only way you can test it through is simulation. Another major advantage of simulations is controlled experimental conditions, which can significantly help in debugging. Suppose you are running a wireless experiment, whether you kept the door open or closed can affect your experiment, and in general you don't want to be bothered by those kind of details, in which case if you were to do it through a simulation, such things don't matter anymore. Of course, there is a price to pay for all these advantages of simulation. Basically, the main disadvantage of simulation is the real systems are way too complex that you cannot capture everything that they do as part of simulation. Now that you bought in why we should do simulations, let's look at the ns2 simulator. ns2 provides a variety of features. It has protocols implemented as part of it, so you can experiment with TCP protocols, UDP protocols, HTTP protocols, routing protocols, media access control protocols, and so on and so forth. Naturally, you need applications that generate data that drive these protocols, so ns2 provides various traffic models. So it provides web traffic models, it provides constant bitrate traffic models. So CBR is useful to model voice traffic, and variable bitrate, so this is used to model video traffic. It provides different error models. For example, you can introduce uniform errors, you can use bursty errors, so on and so forth. It also helps you model physical layer stuff like radio propagation, taking into account the distance and the speed of light, some mobility models, as well as energy models. Naturally, when you are experimenting with protocols in a networking setting, you want to create network topology, X number of nodes connected in a certain fashion through certain links. So this is managed through topology generation. So you have a lot of tools that help you create complex topologies as well. Now that you have generated a topology, developed a new protocol and experimented with this protocol using the simulator, naturally the next question is, how do you know whether your protocol performed as it was intended to perform? In other words, you want to measure certain metrics that capture the performance of your protocol. For this, you need to trace the flow of packets. So ns2 provides a tracing method as well as a visualization tool that shows the animation of what the packets are doing. So here is an overview of ns2 structure. ns2 is basically an object-oriented discrete event simulator. Basically, the simulator maintains a list of events and executes them one event after another. There's only a single thread of control which avoids locking and race conditions. So what do I mean by this? Suppose there is an event that says send packet at node A at time 1. In other words, this event is triggered at time t1. So when t1 happens, you execute this event, and as part of this execution you may calculate what the transmit time is, what the propagation delay is, and then you are going to deliver this packet at node B at time t2, which is probably t1 plus the transmission time plus propagation time. So this you are going to again put it as an event saying receive packet at node B at t2. So this event goes into the queue, or in other words the list. And now when time t2 comes, this event is popped out and it is executed. So on receiving this packet, there may be some action at node B which is executed. That in turn will generate more events which again go back into the list. So this is how this ns2 works. ns2 has a back end as well as the front end. The back end is based on C++, so this is the event scheduler. A lot of the protocols that are given as part of ns2 are implemented in the back end. This lets them run very fast and it gives more control over the execution of the protocol. The front end is a language called OTickle. This is a scripting language much like Perl or Python, which you have probably heard of. This is spelled OTickle. O stands for object oriented tickle, and TCL itself stands for tool command language. So why a back end and a front end? So the front end helps you create scenarios rather fast. For example, in certain scenarios you want to create topologies with 5 nodes, sometimes you want to create topology with 10 nodes. So you want to be able to write this fast and change also fast. So this is much easier to do as part of Tickle. Otherwise you don't want to keep on recompiling certain parameters. So basically for fastness you use a backend C++, and for ease of writing you use a front end based on OTickle. So here is a short tutorial on Tickle. This is very much like any other scripting language. For example, you can set variables in this particular fashion. Arrays can be handled like this. If you want to print stuff, you can do puts. Arithmetic expressions are handled this way. It also provides you control structures, if, then, for, loops, and also procedures. By the way, you don't really need to know the Tickle language to do the lab. I will provide most of the necessary commands. So here is NS programming structure. One of the first things that you need to do is create the event scheduler so that the events can run one after the other. Naturally, a very important thing to monitor the performance is tracing. So a good thing to do is to turn on tracing. Then you create whatever topology you want, you create some connections, TCP, UDP or whatever, and then generate traffic to feed these connections. You can also insert errors, so on and so forth, and then run the simulator. So let me walk you through it. So to create an event scheduler, this is the command that you are using. You basically are creating a new instance of a simulator, so that creates the event scheduler. Now once you have created the scheduler, you can schedule an event. So you set $ns at time this event. So for example, you can set something like this, which is saying that at time 5 seconds, execute this particular procedure. And this procedure is basically a finish procedure that is going to close down all the opened files and is going to execute a network animator. This is the visualization tool I was talking about. And then after you finish whatever, then you're going to start the network simulator. From then on, it starts executing whatever is listed as part of your Tickle script. So if you want to trace the packets, one way to trace everything is to use this command. So you're opening this file and you're writing into the file and you're saying into this file trace everything. Now when you do that, an output file called out.tr is produced, which will look something like this. Now what are these entries? So this first entry refers to the event type. Plus means NQ, minus means DQ, R means receive, and D means drop, discarded packet. This refers to the time in seconds. This is from which node to which node. This is the type of packet. Its CBR means it is using UDP underneath. TCP packet or ACK packet. This refers to the size of the packet in bytes. This is a flow ID, and this is the source and destination process. Between the same source and destination, you may have multiple processes running. They are separated by the dot. Just notice here that this packet has gone from 0 to 2, but its final destination is actually node 3. Within node 3, process 1. So this is the sequence number of the packet, and a sequence number refers to a unique ID assigned to each and every packet. For example, if there is a retransmission of this particular packet, the sequence number stays the same, but this a sequence number changes because it is saying that this is a new instance of the packet. Trace all traces the packet flow as part of the simulation. You can also trace certain parameters belonging to a particular protocol. For example, you can open this file and attach this file to a TCP module, in which case you can trace TCP parameters. So TCP has these parameters which it keeps track of. That way you can know how these parameters are varying over the duration of your simulation. If you want to watch an animation of what is happening, you can open a NAM file, set it to NF, and then do NAM trace all. So what all the things needed for the network animator get written to this file. And once you finish the simulation, you can say execute this, in which case the animation starts running. So here is the meat of ns2, the things that go into the tickle file. So for example, if you want to create two nodes and connect them by a link, you create nodes using these two commands, set n0 ns node. And similarly, if you want to create a link between the nodes, this is specifying the type of link. You want it to be a duplex link between which two nodes, n0 and n1. You're specifying the rate of the link and the delay. This is basically the propagation delay. And you're also specifying the kind of queue that should be employed at node 0. Drop tail means if the buffer overflows, you drop the packet that is at the end, the tail of the queue. Now suppose you want to send some data over the link. So this is the way to generate data. So if I want to use UDP, I'm going to create a UDP agent and I'm going to attach this UDP agent to node 0. And this UDP agent needs some application level traffic, and to do that I'm going to create a CBR traffic and feed it into the UDP agent. So there are a bunch of commands to do this. So basically this creates a CBR traffic source, and for this I'm going to set the packet size to be 500, the interval to be 5 milliseconds. So in other words, in this case, packets get generated every 5 milliseconds, and these packets are of size 500 bytes. And then I'm going to attach this constant bitrate traffic source to the UDP sender, that is UDP 0, which is in turn attached to node 0. So similarly, I want a traffic sink also, which is going to take these packets at the receiver. So for that I'm creating an agent null. Basically this frees up memory associated with the packets, and this I'm creating at the node 1. This is the end point of the traffic that is originating at node 0. Naturally, you need to specify who is the sender and who is the receiver. So here I am telling through NS connect that whenever this sends packets, send them to this particular receiver. And you can also specify when to start and stop the data by specifying when the CBR source should start. It's saying 0.5 seconds start sending the data, and at 4.5 seconds stop sending the data. So this may seem too much information at one go. Just go through the code. It's not very complex. I think you will understand what is happening. So similar to UDP, you can also create TCP connections. So here you created a TCP agent, and you attached it to node 0, you will create a TCP sync agent, which is the receiver for that particular TCP, and you will attach it to the node 1, and then you are connecting these both agents so that you know who is the sender, who is the receiver. Now to feed the TCP source, you are starting a file transfer protocol application. So this is given by this command, and you are attaching this to the TCP sending agent. You can also use another application like Telnet, in which case you will use this command and again attach it to the TCP source node. You can create errors using an error model. So again, this is an error model, and you can specify the parameters of this error model. In other words, error is at packet level, it has a error rate of 0.01, and the type of error is uniform. And when a packet is in error, you also have to specify which agent is going to take that packet. In other words, once if a packet is dropped, it goes to this agent, which will free up memory related to that particular packet. And this particular error model which you have created, you can insert between any two nodes. In other words, the link between these two nodes. I will show you a demo of how things work, but for now what we have seen so far is that simulators help in easy verification of protocols and lot less time and money. And ns2 in specific offers a variety of protocols, suites and scenarios, so it's very versatile. ns2 as such has a front end which is based on Tickle, which helps you easily create simulation scenarios, and it has a back end based on C++, which helps you implement the protocols. This is an ongoing effort of research and development. So there is a new version of ns2 called ns3. I myself haven't experimented with it, so we are still sticking with ns2, but people are free to explore this as well. So here is a demo of how things work with ns2. So here I am in a directory called demo, and this directory has a file called ns-tcp.tickle. As you can see, the extension is tickle. I have written a tickle file. Let me open it. So as you can see, inside this you see some of the commands that I have shown before. So I've created a simulation object. I have defined a color for a data flow, because I'm going to establish one data flow, and here is the trace file. This is for the network animator, and this is the trace file for the regular trace, which traces all the packets. And I've also defined a finish procedure, which basically tells to close the files and execute the network animator once you're done. Now in this example, I have basically created 3 nodes, N0, N1 and N2, and I've set some link bandwidths with some characteristics, and I also am setting a queue size between the node N1 and N2 to equal to 10. In other words, the buffer size is 10. If it receives more packets than this, it's going to drop the packet, and this dropping will be drop tail as listed here. Now just for the NAM, so that the nodes appear neatly, I have specified the positions on how to orient the links. This is not necessary for the simulation, but it gives a good pictorial view. And then I'm also monitoring the queue. Again, this is for NAM, so that you can see what's happening at the queue. Now remember, I have 3 nodes, N0, N1, N2, basically 2 links. Now I'm going to set up a TCP connection. So here is the code for setting up the TCP connection as well as the TCP sync, and then this is the code for setting up an FTP over the TCP connection, and I'm also starting and stopping the FTP at 0.5 seconds and 50.5 seconds respectively. And once the simulation ends at 51 seconds, I'm calling the finish procedure, which will close the files and open up the network animator. Finally, I'm saying run this particular event scheduler or this particular simulation. So let's run it and see. So to run it, I type ns and then the file name. So this is for running. And as you saw, once it ran, it is outputting this particular thing, which is the network animator. But even before we get there, let's see what all it produced. So as you can see, it produced this out.nam, which is the thing related to the network animator, and it also produced a trace file called tcp.tr. So if I open tcp.tr, you can see what has happened. It's tracked what happened to the packets. So here is the network animator. We created a topology corresponding to 3 nodes that is represented here, and you can start the animation by pressing this play forward button. As you saw, as I pressed it, the time started to increase, and this time duration here also shows the progress of time. Note that the flow doesn't start until 0.5 seconds. That is why you do not see any flow of packets. So as soon as this time reaches 0.5, you should start seeing the flow of data. So that's the first packet. In response to it, your TCP is sending 2 packets, and you see here some queue has started to build at node 1. You should also see that the ACK packets are very small. This duration is very small compared to the data packets. These are data packets which are of longer duration because their packet sizes are bigger. And here you can see the queue build up. So this is the queue that is kind of building up as packets are going. Now once this queue reaches a limit of 10, you will see a packet drop. So it will happen soon. There is the first packet drop. So as TCP continues to send 2 data packets, packets keep falling, and TCP is clever in that after some time it will notice that it is sending at a rate that exceeds the capacity, thereby causing congestion. That is why you are seeing the packet drops. It stopped sending 2 packets. It's now sending only 1 packet. So you can fast forward the simulation. In other words, if you want to see what has happened at time, let's say here, as you saw, this is now at 22 seconds, it starts playing the animation from that particular time on. So this is more or less how the animation works. So play around with the simulator and have fun.